So yes, my name is Tanguy Coquio. I'm a hydrodynamic engineer at France Energy Marine, and I will present you a first part of the work that was carried out during this GIP, and that concerned the mooring system design and anchor load analysis. So several objectives were targeted for this first part of the work. So we wanted to answer the question, how does sharing anchors affect the feasibility, design, cost, and reliability of mooring systems for floating offshore wind farms? To do so, we decided to study a 15 megawatt turbines with a semi-submersible floater and 3 different water depths including different layouts in a farm. We developed several mooring systems that are designed with and without shared anchor, and the objective is to compare these different systems, sharing anchors or not. We target also mooring load analysis and anchor load analysis. And to conclude with this part, I will talk to you about the cost implied by each configurations. So the design studied was the Voltern USS floater developed by the University of Maine and with the IEA 15 megawatt turbines, which are both open source design. So it was very relevant for our study to share the information about what we've done here. We decided to target 3 different water depths, 80 meters, 200 meters, and 600 meters. And for each different water depths, we define different type of mooring systems that are more or less adapted to each water depth, for more catenary and semi-taut design for the shallow water depths, both for the 200-meter water depth, and taut leg and semi-taut for the deep water depth at 600 meters. During all the study, the anchor radius is fixed for the shared anchor at 970 meters. For the layout of the turbine, we decided to use a regular layout. So each turbine is spaced with a regular spacing of 7 times the rotor diameters. That permits for us to do the hypothesis that each wind turbine is not affected by the wake effect of the others. We know it's not totally true, but with this kind of distance, we can make this hypothesis during this study. You can see that the spacing is also triangular regular, so each mooring line is predicted at 120 degrees, which is natural for this type of floaters for the shared anchor systems. The possibility of look at the variation of this layout was also studied but not presented here. For each of this, for this particular layout, we decided to look at different metocean cases, implying several states for the turbine. We based our study on the analysis on the specific case of the organism's DNVGL, and looked at production cases, park cases for extreme analysis, and park plus occurrence of fault for the breaking of a line, for example. What was not performed during the study is the study of fatigue cases, and so this is something you must know about the study. Here are the kind of condition we looked at. So in production, HS between 6 and 9 meters with associated peak wave period and current, and also wind. That are the rated wind for the turbine and the heaviest wind for the turbine. Also extreme condition with HS 11 meters, with TP from 13 to 17 seconds and 1 meter per second current and 40 meter per second wind. Also extreme cases, ALS cases with extreme condition and a cyclonic case. So yeah, just to precise for this case, we also looked at different misalignment between the wind, wave, and current. This is why here you can see there is a 12 kind of case, but in total, we looked for each configuration at 32 cases, and each of these cases are run for several stochastic realization of the wind and wave, so 6 seeds by case. For the design, we say that a design is validated when it's performing 2 types of criteria. The first one is a design intention criteria, which is combination of the mean part of the tension and the dynamic part of the tension, and we want this to be inferior to the minimum breaking load. And the second part is a criterion of offset, which varies depending on the water depth. So 35 meters for the shallow water depth, 50 meters for the 200 meters water depth, and 600 meters for the deep water depth. This study was performed by two companies, so France Energy Marine, which I'm part of and representing today, but also EDF. This is why we had two models, two numerical models, and we perform a benchmark with these two models. So on my side, I will only talk to you today about the CIMA models, but you have to know that the Diego models were also used to represent time domain, to perform time domain simulations. So in CIMA, we represented aero-hydro servo elastic coupled models. Strong hypotheses are done with the blade and the towers that are supposed rigid, so no stiffness included in these two parts. The mooring lines are structurally represented with finite element analysis, and the anchors are considered by fixed point in this part of the work. For the aerodynamic, the turbine is controlled with an external controller at Diego, but with an internal control in CIMO. The blades are represented with BM method, and the tower is aerodynamic on the tower is represented by quadratic drag elements. For the hydrodynamic, the floater is represented with a classic potential radiation diffraction analysis with a HDB, in which we add Morrison drag elements to account for viscous drag on the floater, and the mean drift forces are taken into account with the Newman methods. For the line, there is also additional drag considered with Morrison elements on the lines. So you have to know that the objective of this study is to compare shared anchor vs unshared anchor. That's why we permitted ourselves to do this strong hypothesis, notably for example, for the blade and the tower that are considered with no stiffness. But this is the case for both of our analyses, shared and unshared. So this is why this is the comparison that is the point here. I will not go into detail into this slide, but just to show you that we perform a comparison of the model between EDF and France Energy Marine. And so we are pretty confident with the model. In addition to that, the Voltern USS and the 15 megawatt ER turbines are well known in the literature, so we had plenty material to compare with. A few words about the methodology to optimize the mooring design. So as I said, for each water depth, we had a guess of what was the good material to use for each of them. For example, more catenary chain for shallow water depth, and like introduction of polyester for deep water depth. So for each water depth, we decided to look at specific combination of materials and then to optimize this specific combination. The parameter of the optimization were the line minimum breaking length, the overall length of the line, and the section length when it's the case of the shared anchor. The criteria applied were ULS and ALS criteria, as I told you before, and the cost minimization. We have like a macro model for the cost of the lines. When going to the optimization of unshared anchor systems, so regular mooring that we want to compare with a shared mooring system, the additional parameter is the anchor position. So it's fixed for the shared anchor system, but not fixed for the unshared anchor. So we may reduce the anchor radius and then save money save cost by doing so. And then we process with an iterative loop, and we want all the criteria to pass to obtain a design a design that is validated. So as I said already before, we decided to split the cases that we want to study. So I will only introduce you today to the shallow water depth, 80 meters, and to the deep water depth, 600 meters. For the shallow water depth, we have looked at 100% catenary chain system, chain plus nylon system, and chain plus HMPE, which is also called Dynema, and polyester 100% for the deep water depth, chain plus polyester, and chain and HMPE for the deep water depth. Here is an extract of the configuration that were looked at. So you can see that for each configuration, we want to optimize a shared system and an unshared system. Unfortunately, at some point, sometimes the two configurations are the same. So, for example, the two first one, 100% chain and chain plus nylon, are the same for shared and unshared. This is due to the fact that in shallow water depth, we are very pushing the limits of the chain diameters, and so we want to use a lot the catenary stiffness of the mooring system, and so it was not possible to further optimize the unshared system for the 100% catenary chain, for example, because if you reduce the radius, it's not possible to pass the criteria. So for the two first line, it's the same for shared and unshared, and for the last one, we have two type of configuration. I just realized that there is an issue here because you have 2 times the same scheme on the right. I'm sorry for that. So you have to imagine that the anchor radius is fairly reduced for the second configuration on the bottom right here. What is interesting to do is that we managed to reduce a lot the MBL for the system with including nylon. And if you add an important length of nylon, in this case, so the 80.3, you will have to manage an important pretension of the system to stay in the criteria of offset. I can come back to that later. Some insight on the dynamic behavior of the different mooring configurations. So you can see 3 blocks each time here. It's the type of simulation we've looked at. The block on the left is production case. On the middle is parked case when the turbine is stopped. And ALS case on the right, not when there is a failure, but when the conditions are increased and the meteorological conditions are increased. What we can see here is that the offset is kind of similar for each configuration. We are always struggling to keep into the offset, but we managed to do so. And for the tension over the 4 configurations, the catenary chain present very important tension, and so this is why the MBL is as well increased for this case. Second part of the work is on the deep water depth, so 600 meters. What we can see here is that we have 2 types of configuration, shared and unshared, for the polyester and chain plus polyester, and for the chain and HMP, it was considered as not viable, as it was difficult to optimize, and the cost was very increased compared to the 2 previous ones. So I will mostly talk to you about the chain polyester and polyester lines. What we can see here is that it's possible to reduce the anchor radius, and so the mooring lengths for the unshared configuration, which is supposed to save cost. The pretension of the 100% polyester is very low. Once again, we do not intend to produce a specific, a very detailed design for this kind of configuration. For example, we know that it's necessary to add a length of chain at the top and possibly at the bottom as well, or to protect the line with buoyancy or socket if you don't want to prevent friction with the ground. But here the idea is to push the design and to see what can bring this type of materials. So I would say the chain plus polyester design is more relevant, but still it's interesting to look at how the anchor will react under such loadings compared to this type of loading, and what each mooring brings to the systems. Again, if you look here at the offset or the design tension for each configuration, what I forgot to say before is that it's always the extreme conditions, so the LC 6.1 at DNV, for those who know it, that are governing the design. So no implication of the production of the production cases, for example, in this kind of design. And what we can see is that if you add stiffness or weight to the design, you have to increase the MBL, and then you have also a lot of tension in the lines to manage. That will be it for that. A short comparison of all the mentioned configurations. What we can see here is that we have we optimize several materials: chain, nylon, polyester, HMP, that produce both horizontal but also vertical loadings in 3 water depths. And we are pushing to the manufacturable limits because we wanted to prevent to have a cluster of lines because it's less natural for shared anchor optimization. But doing so, we are at the limit of the possibilities for the shallow water depth in particular. If we look very quickly at the cost, so the cost were computed for each line with a macro model, so very simplified model, including the material cost, the connector cost, and the tensioner cost, one every 3 lines. And you have to know that cost does not include anchor cost or installation maintenance cost at all at this stage, but we will see that later at the end of the presentation. And here you have a short overview of the composition of each systems with the pretension, the MBL, the chain lengths, the length of each sections, and the global impact on the cost. So having an important MBL for the chain is leading to the most heavy costed line system is the thing you can remark here. Some observations. So yeah, synthetic fibers provide a significant cost saving, in particular with nylon 80 meters and polyester 600 meters. A reminder, fatigue analysis were not conducted here, so it would be necessary to conclude with the previous point on the cost. Also, we miss industrial knowledge on the long-term behavior for nylon. So this is currently investigated in several research project, and in particular in a GIP called BAMOS at France Energy Marine. So this is something that is looked at, but you have to have that in mind when you look at this type of figures. I will now move on to what is interesting for this subject, so the shared loads at anchors. So you have to know that during this project, we did not perform a time domain analysis with several turbines and floaters at the same time in the simulation. We always targeted on only one floating turbines, and take advantage of the fact that we are running 6 seeds for each configuration to produce the shared mooring loads at the anchor. So what was done is that each line that is producing that is involved in the shared anchor loading is considering a different seed of also a different stochastic orientation, of loading, and the three seeds are excuse me, 3 seeds are combined, and to obtain a combined load time series at the anchor. A strong hypothesis that is done here is that the wind is not correlated between 2 turbines, and waves are not correlated between 2 turbines. So of course, we did not use twice the same seed when we performed the combination. A few more details about this combination methods. So what we've done is that we have 6 seeds for each case, and so it leads to 120 possible combinations, and the combination with the maximum force, the closest to the mean of the maximum force, is chosen. So to explain that, it means that we look at the 120 possible combinations, and so each of these combinations perform a mooring loads, global mooring loads. We look at the maximum for each of these combinations. We perform an averaging of all this maximum, and then we look at the configuration that is the closest to the mean of this maximum. And this is considered as the representative combination for our systems. Just a few images about what is done here. So we have a time domain simulation that you can see on the left here. We are selecting we are running for this particular MetaOcean case 6 seeds, and from these 6 seeds we select 3 of them with the previous method, and then we obtain a global loading. So what you can see on the right is 3 blue arrows coming from a cylinder arranged, which is representing an anchor, and we are combining these 3 blue arrows to obtain the global loading with the red arrows here. Just to mention that this is not the same case on the right and on the left, sorry for that. So taut polyester on the right, and it's a catenary chain on the left. So this is not exactly we are not talking exactly about the same thing. As I said, 32 cases simulated with 6 seed by case, stochastic realization, and that we can divide in several type of analysis. We can see the production case, the extreme case, and the extreme case ALS to finish with. For the production case, we did not consider misalignment, but for the extreme case, we did. So there is some misalignment for the DLC 6.1 between the wave, wind, and current, and this is the same for DLC 6.6. And from the point of view of the anchor, you can see that there is 4 types of incoming MetaOcean condition: in between with no misalignment, in line with no misalignment, which means the environment is coming in front of a line or in between 2 lines, which will impact very differently the anchor because it's pulling with 2 lines, and you can introduce misalignments to obtain intermediate configuration. If you look only at the global loading, you can see, as on the left, time series of loading at the anchor and on each line. So depending on the orientation, you will have 1 or 2 lines that are not loaded at all, or a few very not much loaded, and the opposite for the line that are stimulated by the environment, and you have the global loading. We perform some statistics to then work with the geotechnical analysis on the cycle at the anchor. We mainly focus on 2 parameters: R, also called zeta C, which is the average, it is the mean cycle over max cycle load, and zeta B parameter, which is the hash max over the capacity of the pile. As I said, there is 4 types of loading, and they are leading to very different behavior of loading at the anchor. You can see, like on the top left, for example, when the environment is coming in between 2 lines, the 2 lines are very stimulated in alternance, and so you can see that there is a wide variation of angle at the anchor for the loading, but you have not an important tension or an important loading at the anchor. Still, it can be significant. In the opposite, when you have a meteor condition that arrive directly on one line, you will have very directional loading that is very similar to unshared, to what can see an unshared anchor. The loading will be more important with an important loading, but a very restrained angle variation. When you introduce misalignment, like on the bottom right and bottom left, you can see that you can create kind of intermediate loading configurations. To come back to this table, I will not go into detail with this table, but we can see that depending on the type of configuration, let's say with the material, the pretension, and the type of loading, if it's a vertical loading or horizontal loading, we will create different shape of loading paths at the anchor. We can see that, for example, with catenary chain, we'll have R values, also called zeta C, that is limited and increased with going to chain nylon or 100% nylon configurations. Also, the angular variation can be more or less important. You can see that for the chain design, we will have an important loading variation, which is not the case when you go to nylon, and which is reduced for 100% polyester as well. The fact that the fiber reduce the stiffness are producing less variation than other material as well. And depending on the environmental condition, in between, in line, misalignment, the type of loading will be as well impacted. What to say more about this slide? I think I will go next. A few conclusions about this part of the work. So this work provided, as I said, a wide range of data to represent shared and unshared loading that incurred, which is very useful for the geotechnical analysis that we will see afterwards. Depending on the configuration, loading tabs are of different shape at anchor. We have seen that with the inline and in-between analysis, for example. And also, sorry, I just missed a point. So depending on the configuration, so in particular, if you have a lot of stiffness or a lot of chain, you will have very different shape than with polyester material or nylon material. And as loading time series were extracted from the mooring line design, some type of environment load case are not available at the moment, but are being built for the geotechnical analysis. Meaning for the mooring design, we do not want to look at 360 degrees incoming environment because the mooring design that we looked at were symmetrical, so we mainly focus on in-between and inline environment. But when you looked at in the point of view of the anchor, we can imagine that it's important to look at long-term variation environment with, for example, two successive storms to look at what happened. So this is something that haven't been done in this first work. Now moving on to the way forward of this work. So as I said, it's important to include long-term environment variation to create specific loading paths for shared anchors. It could be interesting to perform mooring layout optimization for specific floating offshore wind sites. So what we've done here is that we created kind of a generic site and see what happened with different meteo conditions. But it could be interesting to look at a specific site with its specificities. For example, in terms of meteor-ocean condition, that can be very directional or bidirectional or multidirectional. Consider also increased risk of failure in the mooring configuration design. And to go further, it would be interesting to include sharing line concept in this analysis.